Hello and welcome to Tvaritam.AI. In this video, we are going to understand ensemble learning and random forest. Now, ensemble learning is a technique where we combine multiple models to improve overall performance. Here, instead of relying on a single model, we train multiple models and combine their predictions. The idea behind this is that a group of weak or moderate models can come together to form a strong model. It reduces the overall variance as models cancel each other's mistake. This improves generalization and such models are more robust to the noise in the data. Now when it comes to bagging or bootstrap aggregating, it is one of the widely used ensemble techniques. It trains multiple models on different random samples of data and averages their prediction. It works in two main steps. Bootstrap sampling, where we create multiple datasets by sampling from the original dataset with replacement. Each dataset here is slightly different. Usually 63% of samples are used in each bootstrap dataset. Second is aggregation. We train a separate model on each dataset, combine their predictions. In classification, we take majority voting, and in regression, we take the average or the mean value. The main goal of bagging is to reduce the variance in the model and make the model more stable. However, in standard bagging, all features are still available to every model, which can sometimes make model too similar. And if all the trees make similar mistakes, that means that they are highly correlated, then averaging their prediction does not reduce error much. Here comes random forest. So random forest is one of the canonical examples for bagging, but here we add an extra layer of randomness to make trees more correlated. A random forest is essentially a collection of decision trees built using bagging with an additional layer of randomness. So each tree will use a bootstrap sampled dataset, and at each split in a tree we only consider a random subset of features. This introduces feature level randomness. This extra randomness helps because in decision trees some features can dominate and appear in most split. Random forest avoids this by forcing trees to explore different features, thus making the trees less correlated with each other, and lower correlation accounts for stronger variance reduction. Now talking about the hyperparameters in random forest, we can usually classify them into number of trees, randomness hyperparameters like maximum features and maximum samples, and tree complexity hyperparameters. Now moving forward with the number of estimators or the number of trees, we define this by how many trees are there in the forest. More trees usually improve the performance but can increase the training time, and after a point improvement becomes minimal. So you can keep a lower value for the number of trees if you want to train a quick baseline model. 200 to 500 can provide you with stable results, and more than 1000 trees should only be used for high accuracy needs, but it may take longer training times. For maximum features and samples, maximum features defines the number of features considered at each split. Lower values lead to more randomness, resulting in more diverse trees, while higher values can lead to trees becoming more similar. Typically, for classification, we use the square root of number of features. So if we have 4 features, we will choose 2. And for regression, we go with features divided by 3. So if we have 9 features, we will go with 3 features in total for the single tree. Then for maximum sample, it controls how many data points each tree sees. You can either use the full dataset with replacement or give a smaller value to increase diversity and reduce computation. Now for tree-based hyperparameters, even though random forest itself reduces overfitting, we can still control individual tree complexity. Maximum depth limits how deep each tree grows. In random forest, it is not as crucial as a single decision tree based model because random forest can allow deeper trees or trees with unlimited depth. Minimum sample split and minimum sample sleeve can have smaller values for random forest as instability is usually averaged out. For leaf control parameters like maximum leaf node or minimum impurity decrease, we limit the number of leaf nodes using maximum leaf nodes. Fewer leaves will lead to simpler tree. More leaves will give it more flexibility. Minimum impurity decrease will allow a split only if it improves the model by a minimum threshold. Now, as compared to a single decision tree again, where the complexity parameters are the main defense against overfitting, as decision trees by themselves are more prone to overfitting, random forest is less prone to overfitting. Hence, the ensemble in random forest itself is the defense for this, and trees can be more complex. Parameters are tuned mainly for efficiency and balance and not strictly to control overfitting. Thank you.